Yes, so I can last but certainly least. So I'm Gianpaolo Carosi. I go at GP. I'm privileged to be also an organizer for this nice workshop. I work on Admx primarily. I'm at Lawrence Livermore National Lab. This is what it looks like when it's not on, when the hills are not on fire. And I've been working on Admx for a long time, primarily working on microwave cavities, but also helping with installation, helping any way I can keep that system running. Yeah, so I think we could probably go directly into it, or I think that's. Yeah, sounds good. Great, so I'll take it away, and my apologies to the theorists. This is going to be very, knuckle dragging experimentalist kind of a talk. So hope you enjoy, but please ask any questions. Hopefully keep this kind of engaged and interactive. So please stop me. So I'm going to skip over, we're all here. We know the Axion's great dark matter candidate, solves Peccei-Quinn, the Peccei-Quinn solution to the strong speed problem. But I always love the vastness of the parameter space that we're looking for. So this is just dark matter writ large, everything from giant, black holes all the way down to neutralinos, sterile neutrinos, and then you get the Axion way at the bottom here. And so that looks totally tractable. We can totally search this region until we zoom in a little bit, and then we realize it actually covers a huge parameter space. And this is the challenge for the experimentalists that we have to really delve into, is how are we going to be able to scan everywhere between kind of the bounds set by supernova 1970A, all the way down to the kind of the lower bounds set by the size of dwarf galaxies. So that is the experimental challenge. I think a lot of us here are up for it. And let's get into what experiments are out there to try and probe this. So first, we need to figure out how can we look for this. I think most people, are focused on the Axion photon coupling. This is actually the one that is pretty well modeled and has very low model uncertainties. So it couples through a loop here to 2 photons. And so that's most of the focus I'll be looking at today. But there's also, Axion coupling to electrons and nucleons, which I will also touch on later on. Okay, so this is actually the whole coupling here. So like I said, I'm going to be coupling mostly to photons and most of the experiments that I talk about here. But for spin searches or quarks, other kind of searches for Axion winds, we may be able to look at other types of couplings. All right, so here is an idea of the parameter space for 2 photon coupling versus the mass range. There's a variety of experimental types we can look for. So we had the laboratory-based experiments, and this includes lasers, like shining through walls experiments, like the ALPS experiment that's going on at DESI. Also fifth force experiments like Ariadne, and I think we'll have a talk either later this week or next week from Andrew Gracci on that. You can also look for solar axions. So these are axions that are generated in the sun. CAST is the prime example of this, has done a lot of great work, set some of the best limits in the world up here. And both Baby IAXO and AXO are going to take over the mantle of that and push those way down. And I'm going to let Julia and Igor and others talk about that later. I'm going to focus today entirely on dark matter haloscopes. So these are primarily, I'm going to be talking about microwave cavity systems. There's a lot of, that's probably the most well-known and well-developed technology, but there's new technologies as well, LC circuits, NMR techniques, and whatnot. And you can see here, we're starting to actually really get into the parameter space. We're actually starting to be able to say whether or not axions in certain mass range are the primary dark matter candidate or not. Okay, so I'm borrowing this slide from Katerina. She gave a wonderful overview, and I encourage people to go check out her YouTube video that was at the beginning of this workshop series during the training series. So this just gives an example of, in red here are all the different dark matter experiments that are currently ongoing right now. Everything from, Abracadabra to Haystack to ADMX, Quacks. They're all listed here. I'm going to try and go through most of these and outline what some of the differences are, and so, some of the part of the parameter space people look at. My apologies if I miss somebody. Come yell at me afterwards, and I'll be sure to include you next time. Okay, so I'm going to start with just the haloscope technique. I think some of you, most of you are probably aware of how this works, but in case those aren't, this is a very different type of experimental technique than looking for wave dark matter, which you're looking for very rare scattering. Right now, we're looking for an axion to come in with a wavelength. We think of it as a coherent field. That axion's coherent field would interact in a strong static magnetic field in which we have a microwave cavity at the same resonant frequency as the axion. So what would this look like? Well, effectively, it would look like a increase in energy at a particular frequency. And it would be enhanced by this, the signal would be enhanced when that microwave cavity signal is at the same frequency as the axion. You can essentially think of this as a glorified AM radio, which is what is the easiest way I think to describe it to folks. So since it's a narrow band experiment, we have to step along at different frequencies. And the name of the game in terms of scanning quickly is this Dickey radiometer equation, which is the signal to noise, which is defined as your axion signal, given here, over your noise temperature or your system noise temperature, multiplied by the square root of the integration time, how long you sit in any one frequency over the bandwidth of your experiment. So let's look at some of these numbers. So the signal you expect goes as a couple of experimental parameters. There's the magnetic field squared times the volume. You want the biggest magnet and biggest volume cavity as you can get for any particular frequency, as high quality factor as you can get, and then what we call a form factor. That's essentially an integration of your electric field of your particular mode for that cavity at that frequency. Generally, that's of order 0.5 or so, but it can go up or down depending on what you're trying to do. And then, of course, there's the parameters Mother Nature gives you, which is the coupling, the mass, and the local density. There's nothing we can do about those. If you put in the numbers for, say, ADMX, along with our anticipated, 0.45 GeV per cubic centimeter and axion masses in the few micro EV, you get about 10 to the minus 24 watts. So that sets our signal power. All right, so let's look at our noise. System noise temperature is something we've been working on for a long time. How do we push the limits of that? And to be an example of what some of the limits are to date for just standard linear amplifiers, you can in principle get down to about 50 millikelvin or so at about 1 gigahertz. That's very challenging, but people have been able to get there now. And really the name of the game is to get beyond that. Integration time has usually been limited to of order a few minutes. And that's in order to be able to scan a huge amount of parameter space as quickly as we can. And one of the things I like to think about these experiments is if we knew where the axion was, this would be a much simpler experiment. We could just sit at that frequency for maybe a day with a modest magnet, liquid, helium-4 or something like that. The challenge is really being able to scan quickly. You can turn this signal noise equation into a frequency coverage at a particular sensitivity equation here. And just to give you some parameters that are important, it goes as the coupling that you're looking for at the fourth power, which shows you how difficult it is to get to lower couplings. You slow down tremendously, even just going from KSVZ models, kind of more optimistic, to DFSC models. For the same experiment, it would have been factors almost 100 different in terms of scan rate. The other big parameters, of course, are it goes as magnetic field to the fourth power, volume squared, linearly with the quality factor, and to the square power of the system noise temperature. So there's a lot of things that we can push on experimentally, which is what has been done over the past 20 years or so to really get into parameter space that we can actually run. And I'm going to show this, I always love showing this one as an example of how an axion kind of couples. Let's see if it'll do it. Thinking. Okay, maybe not. Yeah, we'll skip it. I think I just I got the spinning pinwheel. Oh, yeah, I'm just gonna skip it. Basically, what that would have showed would be an oscillating, signal, which would be axion slowly coupled through a magnet to the cavity axion. We have to coherently add signal power to it, as opposed to a hard scatter like you'd see for WIMP searches. So I'm going to focus on ADMX to start with, because that's what I know and what I've worked on for a long time. This is the ADMX experiment at the University of Washington here. The experiment is based around an 8 Tesla magnet, solenoid magnet. It's a little dark to see here, but it's about 60 centimeters in diameter and about 1 meter in length. And inside is where we have our microwave cavity, usually of order 100 so liters. And we tune that with these kind of microwave cavity tuning rods that we physically move inside. We then have a second magnet located about 1 meter, meter and a half away that allows us to cancel the fields just in this region here so that we can have superconducting quantum amplifiers, low noise amplifiers that are allergic to running in magnetic fields, at least right now. And then we boost the signal up and mix it down to signals that we can digitize on. And the whole system is able, including the bucking magnet, to be removed in and out in this reentrant bore magnet system. And just to give you a scale of time, it takes about a month, month and a half to replace packages and put things back in. And usually we're swapping out cavity bands over a few tens to hundreds of megahertz. Okay, so the enabling technology for the experiment, this experiment started in the mid-90s at Lawrence Livermore Lab using regular HFET amplifiers, pumped liquid helium. The enabling technology was really developed by John Clark when he developed these microstrip squid amplifiers. These were able to get near quantum limited amplification in the hundreds of megahertz range. So that allowed us to actually, for the first time, get to KSVZ sensitivity. And once we were able to show, or I should say DFSZ sensitivity with the first introduction of dilution refrigerator. We've since moved on to parametric amplifiers, Josephson parametric amplifiers. They're essentially a similar system to the MSAs, but with a different layout. They're still using Josephson junctions. But in this time, we have a classic, we have a pump tone that is put in, and using the mixing inside the nonlinear inductors of the Josephson junctions, we're able to increase the power almost noiselessly on the system. And so these are now kind of our workhorse. This is showing about 20 dB of gain for one of our amplifiers. This is just, they're very small in a package, and they run on about, roughly about 20 dB more power than you're looking for. You're looking off of the main frequency. All right, so how do these experiments actually look when you implement them? So microwave cavities are where all the action happens, but we have to be able to know what's going on in the cavity. So for that, we have a system where you can inject signals. You have your amplifier here, and I'll go through the exact way we run them. And then we have some calibration systems. The difference between the microstrip squid amplifiers and the JPAs, essentially the JPA is itself a reflection device where you reflect power off and get gain. So you need a second, what we call a circulator, non-reciprocal device to be able to turn that into a 2-port system. So how do we actually operate these detectors? Well, first we want to know what the coupling to our experiment is. And so what we do is we send in a bypass signal through our directional coupler. These mean that RF signal flows into the cavity, reflects off, and then comes back up through our amplification chain. And so it looks like here, you look at swept signal, on resonance, all the power disappears into the cavity, and then off resonance, it bounces back out there. And that allows you to see how much your coupling to the cavity is. And there's an optimization in which we want to be about, factor 2 overcoupled, beta of 2. All right. We also want to look through the cavity, and this we have a weak port, very weakly coupled to our cavity, in which we can send in swept signals, and then we can see what our resonance structure is. So we do a sweep here, look at what our quality factor is. You can get the quality factor also from the reflection dip, but this allows us to also put in injected signals. So it's an independent measure of the resonance, and then we can use this for synthetic axion injection. Okay, so when we're actually taking data, we just are looking at the cavity of order 100 seconds or so. And we want to make sure that that we have tons of attenuation on a lot of these lines to prevent any other signal power, any other RF leakage. Sometimes you can get radio station interference. A lot of times that happens externally, but we do a we do a careful job of trying to prevent all external sources from coming into our cavity system. All right. And then finally, we have a noise calibration. So the noise calibration is crucially important for this experiment because without with the absence of a signal, we want to know how quickly we can really scan. We would like that noise to be as low as possible to be able to rule out a space quickly and go to the next frequency. So what we have is a attenuator here that we can heat up independently and then look at the whole signal chain and do a calibration of that. That's what we call our hot load measurement. In principle, you can also have a heated attenuator here on this injection in which you're looking at the cavity and you can bounce off the cavity and come back up. That's something we're looking into, but it's a little trickier to do. And we have not actually done that quite yet. And so we do this semi-regularly to make sure that we understand what our noise performance is and look at our signal noise levels. Okay, so how do we actually move things around? There's some mechanics that go on here that are somewhat challenging. The two mechanical systems we have in the current Admx are these gearbox systems that have about a 1 in 19,000 gear reduction in order to move about a kilohertz steps at a time. So it's a double worm gear system that then couples to a sapphire axle that then moves the tuning rod internally towards the edge of the cavity and then back towards the center. In addition, as we slowly move over frequency space, we have to optimally couple the antennas. So we have a similar system that works on a rack and pinion. It allows us to very carefully couple the antennas both in and out. And we can also pull them out and look at systems when they're undercoupled. All right, so when we're looking for axions, we're actually taking data. We have a near real-time analysis and then an offline analysis. And the way we do it is we scan at a certain signal noise level and we look for anything above a certain threshold. And there's a couple of different noise signals that we can see. One is just a statistical noise source. For example, we can see in blue here, that's our first signal, and then orange is the subsequent rescan. You can see that the statistical anomaly that went above our threshold was not seen in the subsequent scan. However, we did see one that was persistent, and this particular one was from a blind injection. We have a blind injection team that's able to send axion-like signals with specific waveforms and power into that weak port antenna, and they typically do not tell us where they are when they're doing them. There's a subset of ones for calibration that we use, but then there's ones that we just don't know about, and we need to be able to see, and it shakes out our analysis system. So I'll give you an example. When we were running for Admx Run 1C, we run in different phases. The Run 1A, B, C, or just different frequency bands. This one in black here is a TM010 mode. You can see as we move the axions line width, and usually we have a 50 kilohertz bandwidth that we digitize on. The axion line shape is much smaller than that. And you can see as we move the axion, the cavity frequency, you can see power increase as we went on resonance and then decrease as we went off resonance. So this was really interesting. The signal had a line shape that was consistent with the axion. Power went away when we were off resonance, so it wasn't consistent with radio frequency interference. It responded to the cavity. So we were very excited about this. So we decided to look at the TM010 mode also. So the TM010 mode is this one. This is the one that should maximally couple to the axion. The magnetic field and the electric field are aligned for this mode. About 10 megahertz away or so, the TM011 mode has a node here. And so axion signals, if you integrate this entirely, would cancel out. And so you have no effective coupling to the axion. So we looked at that one. We just moved the cavity frequency to the same spot, and we saw that signal persisted, which means it is an injected signal. So we were sad. We put the beer back in the fridge, and we moved on. But it's a nice way to keep us on our toes and be able to say whether or not we're actually seeing real signals or not. Okay, so where are we now? So ADMX has been running for in various phases since the mid-90s up until recently with our dilution refrigerator as part of the DOE's Gen 2 project. We've had 3 data runs, effectively 3 data runs, and just finished up a 4th one. And those come in the blue. This is run 1A, run B, and run 1C. And we've gotten to DFSC sensitivity all the way up to about 1 gigahertz or so. And we finished a data run this last year, and we're getting ready to finish the analysis for that. And we're prepping for the next phase as we move up in frequency. So this red band was actually the first time we looked into parameter space beyond previous ADMX runs and below, CAS sensitivity. All right, so the next phases that we're looking at, which we're getting ready for in the next month or so, is this what we call run 1D. This is replacing these tuning rods here with a larger tuning rod that we completed testing at Fermilab this last year and is getting ready to be installed, I think, next month. That system right now should get us about close to 1.4 gigahertz over about a year and a half or so of operating. And then cavity 2, A and B, are a 4-cavity array. And the idea of going to the 4-cavity array is that we can coherently add the signals of the Axion from each cavity if they're locked to the same frequency. And so the noise itself adds incoherently. And so that is currently in testing phases right now. That's expected to start running at around 1.4 gigahertz in about a year and a half or so. Okay. All right, so what's next? What do we do after this? We have this plan now to go up to 2 gigahertz, but we were continually looking towards the future. Well, one of the things we've been looking at is enhancing the quality factor of the cavities. Loaded quality factor for copper is about 40,000, below 4K in this region. But there's been some really, really cool research that's been done both at the Korean group, the Center for Axion Precision Physics, at Korea. They've been looking at YBCO, and then the Quacks group has also done some really nice work with niobium titanium cavities. And the general idea here is that you have superconducting cavity that's parallel to the magnetic field. You don't have the high RF losses that you would get for the material when it's perpendicular to the field, which is really what's been limiting that for like accelerator magnets. So we're looking to implement these results. This is some results in the Quack group showing enhancement relative to copper, as well as the CAP group has gone up to about, I think I'll have a slide later showing even up to 13 million or so Qs. And the clamshell designs there allow for easier sputtering or adding of layers to that. Okay, so what other knobs can we turn? Of course, the other big one is magnet. What kind of magnets can we get? So the University of Washington's magnet, the B squared B is roughly around 12 or so. This was a system that was bought in the mid-90s from a local NMR company. So it's been around for a while. It's been a workhorse, but we need to look at other stuff. If you just look at what's out there, I don't think we're going to get Eater's magnet anytime soon. I think it's busy for a while. But we would like to build up in the magnet space. We do have a magnet that's coming online that is about an order of magnitude more energy for ADMX. And that's what we're basing what we call ADMX extended frequency range around. So ADMX extended frequency range is part of the DOE's Dark Matter New Initiative program. And I'll show a couple other experiments that are part of that program. The basic idea here is that we're scaling up the system. We're scaling up the complexity, but we're kind of brute forcing this. We'd like to gain, by going to roughly 18 cavities that are co-tuned at the same frequency. We're going to be actually in phase amplitude combining digitally. So each cavity itself will have its own low noise quantum amplifier chain. And then at room temperature, we're going to be mixing those together and adding the signals up. And the idea here is redundancy. We have more space with this new magnet system, which I'll show you in a second here. And so if one cavity, for example, goes down, we don't have phase mismatches like we would if we had passive combiners. So we trying to take full advantage of the coherence of the Axion signal. This magnet was a really nice find. This is a magnet, NMR MRI magnet 9.4 Tesla system with an 800 millimeter bore. It has 140 megajoules of stored energy. And that's being moved to Fermilab in the next year or so. So this is what the system should look like in the end. We are going to be putting this, we're going to have a passive shielding. So instead of having a bucking magnet, it's going to be just large stainless steel, similar to what's already installed for the MRI magnet at the hospital that it's being removed from. There's going to be a dilution refrigerator specifically just to cool the magnet system, the cavity system down. And we have, because it's a horizontal system, that provides some challenges, but some opportunities. We can get to both sides. We can slide it from this side here as well. There's going to be photon transport. So it's about 5 meters from here to the quantum electronics packages. Those quantum electronics packages are going to be kept at about 25 millikelvin or so versus the 100 millikelvin for the cavity system. And one of the challenges has been finding cables, very, very low loss cables. Every small bit of attenuation is photon loss. This problem, I think, has been solved. We found very large copper air core cables. We have the space to be able to put those in order to get the photons transported from here to here, where our quantum electronics packages are. And this is essentially just a scale up of the ones we've been using so far. Washington University St. Louis has taken over the quantum amplifier and JPA construction. Yeah, please. Yeah, so that's a good point. So one of the things we want to make sure is we have very little loss. We have, I think, 0.5 dB is the maximum amount of loss we have, and the cables we've tested show around 0.4, 0.43 dB of loss. And so every time you lose photons there, you're going to also replace them with noise photons, and these cables are all still kept at like 100 millikelvin or so. So that's still pretty minimal, but it goes into the entire simulation of our noise performance and how long it takes to integrate. And so the calibration of that with either injected noise sources or individual heated elements at the cavity stage is something we have to carefully implement. Yeah, it's certainly a concern. Yeah.
Why do you want to be so far from the magnet?
Yeah, so it's basically just, this is a huge MRI magnet. The fringe fields drop off. It's a solenoid, but it drops off somewhat slowly. So the question was whether or not we should get a bucking magnet to cancel the field close by, versus trying to just do the passive shielding like they have now. In looking at how expensive it would be to make the bucking magnet, the choice was pretty clear. We should just go with the stainless steel. It's still going to be about $1 million worth of stainless steel. But compared to the complexity of the magnet, we're trying to keep things simple as we can. So we just need to negate the field enough where we can use passive shielding on the outside for the quantum electronics. But it's certainly something we had to consider. Other questions? Cool. Okay, so planning. We're trying to plan this so that this system is ready to go as we end our operations with the system that's running at the University of Washington right now. We're looking at around a total runtime of 3 years, and we're expecting a 2-year construction. It's been pushed back a little bit because DOE is trying to get their funds together for it. So we're still in a design phase right now. But the idea is to begin 3-year operations kind of FY27 or so. And we're looking at enhancing the scan rate and sensitivity with some superconducting cavities as well. So this is where we're hoping to apply some of the superconducting either YBCO or Niobium 310, and working with folks at Fermilab to implement that.
Is the quality of these cavities the current quality of the cavities?
Yeah, so right now our baseline design was assuming just copper. And we showed with the large volume we have that we can hit our target. Now, if we were able, right now we're in the kind of a design prototyping phase where we're going to try out some superconducting. And the nice thing about that is we have a couple of choices. We can either go more sensitive. Alternatively, we can maybe have less cavities if that works, and open up the space so that we can do some maybe higher frequency stuff. One of the design things we did with these cavities is by keeping the clamshells the same, we can adjust the tuning rods on the inside to change the frequency range. So you could possibly have 12 of the cavities in one frequency band, have a slightly different tuning range, and have 6 of the cavities in another 9 and 9, something like that. So we're looking at optimizations for the being able to scan that range as quickly as we can. Okay, so there's other things that are being looked at as well. So that's kind of the Dark Matter New Initiative kind of baseline program. But this is a large magnet system. If we're done with the ADMX magnet in Seattle, maybe there's other experiments we could do in that. One thing our collaborators at Stanford and SLAC have been looking at is what they call Admx Vera. I think it's a recently named thing. And for details, you can ask Chelsea about this. But this is an idea that was also pioneered by Chaolin Kuo. It's an idea of a different cavity geometry. So in this case, the resonant cavity exists between the inner wedge and an outer shell. And then basically this gap sets your frequency. So you're constraining your mode kind of inside that range. And the idea here is trying to have a simple tuning mechanism in which you can move in and out, have a good frequency shift over time. The challenge of this, of course, and the nice thing is it's compatible with the magnetic solenoid fields. The challenge of this, of course, is keeping things well aligned and making sure whatever geometry you have here it doesn't have mode leakage. But they've looked at specific implementations of RF chokes and other mechanisms. And they're in the process of setting this up at Stanford and SLAC. So this is an example of what their in principle range would be. I think they're looking at a dark photon search to begin with. They're going to start with a warm run and then planning a cold run after that. And they're doing a Dilfridge or a 4K system. Dilfridge, nice. And so here's some of the parameters. At room temperature, you get Qs of about 5,000, go by about a factor of 4 for ordinary coppers, you go to cryo. And then they're looking at doing this in a dilution refrigerator with some students as well. There's a graduate student here looking at doing different haloscopes using precision metrology. And one hopeful idea when ADMX finishes up at UW is to perhaps put one of these large cavities in there and do a dark matter search. So I'll show another figure in a little bit because another group is using a similar system, but effectively the mode is, it's like a TEM010 mode in that direction. So there's a form factor that you take a small hit from the angle, but that's about it. It's still decent. Okay. So I'm gonna move on from ADMX for a moment. I'll get back to it when we get to some low frequency stuff, but I want to talk about other haloscopes that have come online over a number of years, please.
I didn't actually follow for the Admx Vera.
Yeah.
What advantage is there in this configuration?
Higher frequency and a pretty decent frequency band coverage that you can do. And the quality factor, right? Yeah. Yes, volume enhanced resonant Axion.
I see. So if you had on a square or cubic size thing that you have problem, then you wouldn't bet on it.
Yeah, there's some really cool design. To his original paper, I'm not sure if I have it here. Exactly. Yeah. Yeah. He had these really cool brain cavities that kind of like look like these fractal structures and such. So, yeah, so it's a cool. I would encourage you to check out Chaolin's paper. I think I've referenced it later as well. Other questions or? Okay, so let's move on to the CAP program. So this is the Center for Axion and Precision Physics in South Korea. This is multiple experimental efforts. It was a large center It still is. So there's a question about what the status is moving forward, but I think Giannis will be here next week and probably answer more questions about it. I don't know. I do know that they've done some really cool stuff with both cavities, including these multi-cell cavities, what they call the pizza cavity, to try and look at higher frequencies. They have a higher field magnets. There's a 12 Tesla system as well as an 18 Tesla system. And as I mentioned before, they've done some really cool stuff with YBC superconductors. In fact, one of the things I really liked, well, actually, I'll come back to that in a second, but they've recently demonstrated DFSC sensitivity. So we've welcomed them. Admx and Casper and other elements have reached DFSC sensitivity in these frequency ranges. They scanned around 20 megahertz, but they're continuing to scan now, from what I understand it, and hopefully we'll be able to scan that frequency range soon as well, looking at about 25 millikelvin base temperature. So here's that PRL for that recent result. Yeah, this is the thing I'm really excited about. So this is some third generation cavities using this particular high TC superconducting tape. And they were able to demonstrate, this isn't published, I haven't seen it published yet, but I've seen it in slides, Q of around 13 million at 8 Tesla, which I think is fantastic. Yeah, exactly.
Changes completely.
It does, absolutely. So that's the caveat there. Yeah. So it's interesting. They're planning, I guess they're trying to implement this into the 36-liter cavity for their 12 Tesla system. And they've started making inroads both in apps, and they've come down to DFSC sensitivity and a few KSV sensitive experiments. But these are the things I'd love to talk to them more about for the YBCO, or I should say the other tape. Okay, so other experiments that have come on, there's a huge parameter space, and so the nice thing is if you just pick a frequency range, you can make good science, and perhaps this is a divide and conquer strategy in which we can look at the frequency space. So this is a Taiwan Axion search experiment that just had results out last year. A similar system using microwave cavity here, copper cavity, 8 Tesla magnet. This is a Blue Force system AMI magnet that you can buy kind of off the shelf. They're looking in the future, and they've been working with Chaolin also at Stanford to implement a similar kind of system to the one that's being developed at Stanford. And so here you can see this is like the electric field there for their structure for a similar kind of wedge system that kind of moves up and down in there. Yeah. This one's a smaller. Oh, I think that's a misquote. Yeah, that should be serious. No, that's nothing. It's tiny. No, I think that's a mistake. Yeah, let me. Yeah, it's much bigger than that. Maybe it may be actually 68 millimeters. I think. Yeah, so 6.8 centimeters. So they have recent results out. So this is the results here, close to our small sidecar cavity region, and I think they're continuing to move up in frequency. A lot of these came from the UCLA Dark Matter. So if each one of these is from its own talk. If you want more details, please check out the UCLA Dark Matter talks that were done earlier this year. There's the Oregon experiment. This is the oscillating and resonant group Axion experiments in Western Australia. They've been looking at really cool new cavity geometries using sapphire. There's Mike Tobar's group and McAllister. Their initial experiments are aimed at kind of the 26, 27 gigahertz range, pretty high in frequency space, kind of up here. And their ultimate goal is to search between 60 and 200 micro EV. There are 2 phases. Right now they're doing kind of 1 gigahertz scans with HVAC amplifiers, and then eventually move into wider scans broken into 5 gigahertz chunks. And you can kind of see that full program here. So they're starting right kind of in this range with 1A and 1B. Ultimately, they like to get down to DFSC sensitivity. That will require very efficient kind of single photon counting in this region, which has a lot of development still to do. But please see Ben's talk from UCLA. Okay, I'm going to briefly flash this just to make for completeness. We saw this wonderful talk earlier this morning, so I won't dwell on it, but I think it's a very cool technique. And And I'd be very interested to talk about other ways of enhancing that signal, maybe with the superconducting wires. So this, I think, was shown earlier. This is the phases for the alpha program. Again, I'm not going to dwell too much on this since we talked about it earlier today. Okay, so we've laid out a lot of the experiments that are out there right now, at least in the cavities. I'm going to take a quick shift to talk about what's slowing us down. What's slowing us down as we go to higher frequency is the quantum limit. Everything we've talked up now has been using linear quantum amplifiers. So we're bounded by the noise floor here of about at half a GeV, 24 millikelvin. We're pretty much at least for Admx thermally dominated. As we go to higher frequencies, 5 gigahertz or so, now we're at about a quarter of a Kelvin, and if we try to go to 20 gigahertz, we're really going to be dominated by the quantum limit there. So how can we get past that? We can do squeeze states perhaps. And I'll show you a little bit what Haystack has been doing, and then single photon detectors. That would be the ultimate goal. Okay, so I'm going to touch back with the Haystack experiment. So Haystack is an experiment at Yale. It's about a few liters cavity. They really made it for a kind of a test bed. They've published data with standard searches, but they've also done some really innovative stuff with squeezing. So here they've actually been able to squeeze the noise. So they've had a squeeze state injection, which allows them to squeeze the reflected noise and increase the bandwidth that they're able to see any Axion signal coming out of the cavity. So this has been demonstrated. They were able to get factor of a few enhanced rate in the scan rate. I encourage people to check out their initial result there. They've also, so here's some actual in blue, what they've been able to achieve with that. There's also a new paper on 2-mode squeezing. In principle, this should be able to get 15 times enhanced. It's a way of doing non-demolition by having another cavity at a different frequency and swapping the states back and forth. I don't really have time to kind of go through that right now, but we should talk about it. This is the ceasefire paper that you can see right here. Okay. So ultimately, what you'd like to do is go to photon counting. So if we can get rid of the phase signal entirely and just count the number of photons, we can go from being in that limit with the uncertainty principle down to kind of the limit from just shot noise. And an example of this is just looking at all the energy, all the phase information here, and just looking at your amplitude. There were some initial experiments done in the late 2000s called the Carac experiment that looked for Rydberg atoms to do single photon counting. They did some demonstrations, but never actually did a full kind of search with axions. As I understand, this is being updated with the Ray experiment that Reina Miyama at Yale is leading as part of the quantum program that's being funded out of DOE. Another way, instead of just using Rydberg atoms, ultimately we would love to use Transmon qubits. So a qubit, especially artificial atom, and there's ways that you can set these up in a separate cavity system. And this was demonstrated in this paper here for dark photon search, in which they were able to, couple to a storage cavity. This is where we'd expect our Axion signal to eventually be generated, and then read out with this Transmon coupled readout cavity. And there you can do quantum non-demolition, where you can continually check to see, is there a photon in that cavity, continually checking that over time and beating down the statistics to say whether or not yes or no, there's a photon in there. The challenge, of course, is that these are superconducting devices, and it's very difficult to put those near magnetic fields still. So being able to do that, yeah. No, so they have a separate, it's kind of hard to see here. Oh, I think I got cut off, I apologize. They had to do there's photon transport effectively. So they still had to do photon transport out of a B field region. So a lot of this has been trying to look at itinerant photons and be able to do photon counting on those. And that's very difficult. There's a lot of background noise if you look at the single photon detectors that you can do still have a huge dark photon count rate, and that's the biggest challenge. Okay, but they have done, at least for this dark photon search, been able to very quickly exclude this band here, over I think a few hours or so. Now, if we can get these to work, you can get a tremendous scan rate improvement. So these are some estimates that were relative to physical temperature at different frequencies. So if you look at 5 gigahertz, 7 gigahertz, or 10 gigahertz systems, you look at the ratio between your signal noise ratio with single photon counters over signal noise ratio with linear amplifiers. So anything above 1 here, you're winning with a photon detector. Below that, you're going to be winning with a linear amplifier. And so typically we've been running ADMX in this region here at around 100 millikelvin to 150 millikelvin or so at lower frequencies. If we can get down to very low temperatures, get our photon backgrounds low enough, because you're basically eating all the noise in your system as well when you're doing the photon counting. So you have to try and move that as far down the curve as you can in terms of you want things as cold as possible. Even at 5 gigahertz, if you get down to 50 millikelvin or so, we'll be dramatically winning with photon counters. Okay, so I'm not going to touch more really on the photon counting side. We need the new technologies. I think there's a lot of promise with some of those, but there's some other options that we can look at as we go up in frequency. And so I'm going to shift to from cavity systems to systems that are induced radiation from conducting surfaces. So in a sense, instead of having a resonant structure, we're just relying on the axion being emitted when the magnetic field has an interface here. And so this is an example. So a good write-up of this was the dish antenna idea with Linder, Jekyll, and others, Redondo as well here. And the idea is that you have this surface here that has a dielectric discontinuity, and in a high magnetic field, you can get axion emission off the surface. Radiated power from a single dish antenna was relatively low. So everything was looking at on the order of kind of 10 to the minus 26 watts for kind of a 10 square meter system with a 10 Tesla field around it. So still very low power. The nice thing about this is you don't need detector tuning. This is a broadband experiment. And so you can use different detectors to try to look for that. So this has gone through a couple of different iterations. I think, for instance, one example, they had open resonator design that Gray & Company at University of Washington put together called the Orpheus experiment. This is a tabletop project that was done. And that is, I think in the next phase is getting ready for magnetic field tests. So it takes an open resonator system, and you'd think an open resonator like a Fabry Pro, you're going to have zero coupling because all the fields cancel out. But if you put dielectric stack in there, you can squeeze the field and every wavelength or so, and you can get a net positive coupling to the axion. And so you put this into a dipole, and then you have an axion signal that can come out. So this is a tabletop experiment that's being worked on. A larger version of this can be thought of as MAD-MAX. So MAD-MAX is the magnetized disk and mirror for axion experiments. The idea here is that you also use these plates, but instead of having a Fabry Pro, you have a single mirror that then focuses the power down to a receiver chain. And so this is currently in the prototyping phase. The ultimate goal is a 10 Tesla dipole with about 80 disks that are then tuned together to move in frequency. Is it kind of a semi-broadband in which they have enhancements given by the wavelength structure of these dielectrics. Okay, so they're in kind of the prototyping phase, as I understand it. There's a 100 millimeter size scale. They're doing some room temperature tests in a dipole magnet at CERN. They've verified some boost factors that they've seen in these, and obviously it's a warm systems test, so they're not expected to beat CAST, but it's a good proof of concept as they go toward the next large phase. So here's their kind of overall plans. Ultimately, they want to be sited, I think, at DESI with a large kind of 9 Tesla, 1.35 meter dipole system. This is a very challenging dipole, but would be a very cool and unique system. It's in prototyping right now, as I mentioned. I think the full size system they expect to hopefully have by kind of late 2028, 29 or so, and start taking data kind of in this range here, around that time frame or so. So another variation on the theme of reflecting is, let's say you don't want to use a dipole, let's maybe use a solenoid. So one way of doing it with a solenoid, in which you have a mirror, a cylindrical mirror where all the rays are going towards the center, is that you can then use a parabolic mirror on the inside to reflect the signal up to a focal point at the very top. And this is the bread experiment being led by Fermilab. The idea here is that you can use this and you can have different types of photon detectors at the top here. This is kind of it's agnostic to which detector you're using. You're just focusing the system here. So there is strategies on the detection side. You can do heterodyne and look for RF, standard quantum limit. They're also looking at both bolometers and single photon counters, such as nanowire detectors. These nanowire detectors are very exciting because they have dark photon count rates that are even below 1 photon, or I should say, dark count rates that are below a dark counted per day for these detectors. So here's some prototyping that's been done at Fermilab. There's kind of 2 experiments that are being worked on as LDRDs in parallel. The first one's called GigaBread, kind of a 10 to 20 gigahertz experiment with just HFET amplifiers and a horn antenna. And you can see this is the inner parabola that's been built for that system. And then there's InfraBread here, which is looking more on using nanowire detectors at around 800 millikelvin to look for single photons. And this one requires kind of diamond turned mirrors on the inside. It's a little less stringent for the RF one. The first experiments are going to be done, I think, in this 4 Tesla MRI magnet at room temperature. This is the projections for one day. They should be able to beat CAS limits with about a year of data taking, even at room temperature, which is exciting. Ultimately, they'd like to have this 1 year 4 Kelvin 9 Tesla system. So they're looking to install this in that large MRI magnet that we had either directly before ADMX or to the side of ADMX, since we have about, I think, 2 meters of usable space there. So for instance, if the superconducting cavities work and we can use shorter cavities, then we have more space for a bread type experiment. Here's some sensitivity limits here. I'll just leave this for dark photons and axions. How am I doing on time? Getting close. So these limits here, note different types of either like transition sensors or kinetic inductance detectors, quantum capacitance devices, superconducting nanowires, different detectors. It's really agnostic to what detector you're looking for, depending on the band you're looking at. And there's a so the magnetic field is certainly an issue, and so part of it is also just moving them outside and having these be itinerant photons. So focusing them out, and there's some looking at the optics. But yes, the magnetic field is certainly an issue for some of those detectors as well. Okay, I'm going to switch back to kind of lower frequencies now, actually. So we've talked kind of about the higher frequencies or broadband searches. Let's go back and look at some of the lower frequencies. So this is the work that actually, Pierre Schivi and others at Florida worked on these reentrant cavity designs to look between kind of 600, as we showed before. The ADMX experiment kind of ended around 600 megahertz. It's a very interesting parameter space to still go lower. So this is an example of a system where you move in and out with the a tunable stub, essentially, and you get a few hundred megahertz of frequency insertion. You do have a hit from the form factor as you move down in frequency, so you have to take that into account in terms of optimizing your scan rate. But I'd point out to this paper that's on the archive now. Even lower than that, you can look at using an LC circuit. You essentially get rid of your cavity system, which and then use an actual lumped element device. So this is the Admx SLIC experiment. Has a PRL here from a while back, but they did some proof of concepts down in the a few hundred about a few megahertz range, few tens of megahertz range. And so in principle, you can go lower. The main experiment that's been utilizing this is really the kind of abracadabra and DM radio experiments. So abracadabra is an experiment out of MIT originally, used a toroidal geometry. So try and look for axions much larger than the size scale of the experiment to try and look for an induced signal in the LC circuit. They did a proof of concept experiment. There's an original paper here, and then they were able to get close to the CAS limits, not quite there, but this is the proof of concept. This is from Chiara at MIT. Since then, they've joined the DM radio group, and so they're working a similar project, and I refer to Chelsea, who's also working on DM radio, to give more details. I think right now they're focusing on this 50-liter system and quantum testbed. Eventually, they're gonna. This is part of the Dark Matter New Initiative program, much like Admx EFR. This is a cubic meter system that's being developed right now. Primary goal of that is to get down to about 30 megahertz, between 30 and 200 megahertz. And then eventually maybe you can get down to the QCD band around 5 megahertz. Ultimately, I think they would like to get to what they call DM radio gut and get down to DFS sensitivity all the way down to about 100 kilohertz or so. Here's some slides that I cribbed from Maria Simonskayev at Stanford. So this is they have a horizontal Delfridge that they're going to be implementing this in. They've been building some of the detector and receivers models right now, and they're getting ready for this 50-liter system. For the cubic meter system, they're in the design phase, much like we are with Admx EFR. This is a coaxial system in a completely new magnet system that's being designed. And the idea is that they'll have different phases of coaxial sized experiments that will have a certain frequency range coverage up to around 200 megahertz or so. And this is their program schedule. So right now they're kind of in the design and construction phase, or I should say, design and construction phase for the 50-liter, design phase for the cubic meter, and ultimately they plan on running kind of 2027, assuming DOE gets their act together. Okay, so I think we're getting not going to take too much more time, but I do want to talk about the Casper experiment. This is to get to very low masses. So this is using coupling to both the gluon fields through Casper electric, or coupling to fermions through Casper wind. And Dima Budker and Peter Graham's papers right here are kind of the initial concepts for this. So they really would like to get down to microhertz of frequency, content frequency. Boston University, Alex Shushkov is working on primarily the Casper electric using spins and some solids. This is for the electric field measurements. And then in Mainz, they're working on the Casper gradient, looking at the wind with hyperpolarized liquids. Right, so this is the primary team there. So Peter, Surjit, Derek, Kimball Jackson, and Dima, thank you. Of course it's Dima. And they're working hard on that right now. This experiment's very cool. It uses NMR techniques to look for the Lamor frequency. Once you've matched the Compton frequency, and you get a resonant enhancement. They're using the squid readout to be able to look for the resonant enhancement. They change the magnetic field until they get to where the axion should couple to, and then they'll get a resonant enhancement in a squid loop. That's the ultimate goal. You can do the same thing with this axion wind. If the gradient is being provided by the axions themselves, you can presumably see that also with the same kind of squid loop readout. Yeah. Okay, and last but certainly not least, Quacks is also looking for the Axion wind, but it's looking for the electron signal. So one of the things, I apologize, this is a bit of an older slide, but this is using, this particular one used a magnetized sample to look at the Lamar frequency. And I would refer to this, paper in the Physics of Dark Universe. They're looking for the effective magnetic field associated with the Axion wind. And this is the one that I think developed the superconducting cavities for even with the gigaspheres as well. Okay, with that, I think I'm just going to end. So I just want to say, there's a tremendous amount of excitement going on right now. The Axion solved the strong CP problem, very good cold dark matter candidate. There's a huge amount of Axion experiments that are coming online. I wasn't able to even touch on all of them. We are already probing parameter space and have very good ideas to probe even quicker. And we're leveraging a lot of the new quantum-enabled technologies that are out there, a lot of work towards single photon counters and the like. So potentially we'll be able to discover or at least rule out large parts of parameter space over the next decade or so. So with that, I'll take any questions and happy to answer anything. Thank you. Yeah.
So you mentioned
Mhm. Yes. Yeah. I mean, that's just to characterize, make sure that like you haven't gone past overcoupling, and just to qualify how good the Q is for particular modes. Usually we have it critically coupled or even overcoupled slightly. You can sometimes get fooled if you're in a strange position or you're close to a mode crossing, where if there's a mode mixing, it is sometimes useful to be able to pull it out and look at it very weakly coupled. It's just for characterization, really, not during actual operations. Yeah. Mm-hmm. Sorry, say one more time. We are testing how well isolation we can have with those, and as long as it's well isolated, 20 dB or more, you're fine. Yeah. So but it is a concern if we have mode leakage between them. It may be an issue, but usually that's just for character when we're trying to characterize things. As long as we have good 20 dB or more of isolation, it's probably fine. Yeah. The good question. There's some placements. I think they showed that. I don't know. I can go all the way back there, but it was kind of like in the top kind of corner. I think is that where they've been looking. They've been optimizing this, like where to put those antennas. Yeah. So like, I don't think they show it. Well, they show it. So for this is the power search. They have a quarter resonator. Sorry, quarter wavelength choke here. And I'm not sure if they have the antenna actually laid out. I don't see it. So it's a good question. I think they've really been looking at how to place those, where to place those exactly to optimize the coupling, but also not get leakage, both leakage and such. So it's challenging. Yeah, a lot of the challenge was also on the fact that you have a large structure that has a moving part, so you can get, which is why they have to try and do a lot of good engineering on the chokes to make sure modes don't leak out.
If you go to slide, I think it was 49 or 50. You showed something that's like I just clarification. No, but it was a line. At one point, I think you were showing maybe bread or something. No, bread. Matrix.
Okay.
I think that was a line called Bushman. By that you mean the nature paper that came out about the window for post-inflation Axion? That's what you were.
I think so. Yeah, let me go back to which one you're talking about. Like you're talking about bread here.
Just a push one, but I think
I'm not sure. I'll have to go look. I think that's this is the QCD stuff that were there. Yeah,
it was
it was a prediction.
it's like problem was the range of that's like a prediction on from
Oh, for strings. Okay.
but I wonder if yeah, that's exactly what I meant because it was just a prediction and I think you meant that.
Okay.
It's very narrow band, but then obviously
I'm not seeing it here. I'll have to look through and find out which one it was. But I think you're right. It's one of these predictions that if there's the alphas. Oh, it was an alpha. Okay. I think you're right. Yeah. Yeah. So. Oh, there we go. There we go. Oops, come on.
Yeah, that's what.
Yeah, too fast. Okay, there you go. So right there. Yeah, I see. I see. Oh, okay. That was that prediction, and it's from strings. You said, yeah. Of course.
Different.
Yes.
Groups that find different.
But this is from the lattice QCD lattice like calculations, or is this for strings? No, it's just
a prediction from string.
oh, from strings. There's okay. Okay.
For post-inflationary.
Post-inflationary. Yeah. Okay. Mm-hmm.
Yeah, for example, yeah.
Ah, okay. I do love having targets. Like it's nice to be able to like. So the challenge to the theorists to give us more like specific targets to look for. Yeah. Other questions or yeah, please. So we look at signal to noise ratios. That's more we do more often, but we usually use that hot load measurement to really calibrate to that, and we have a good idea of some of our amplifier noise. And there's a model I can go back to. I don't know the full details of it, but so the receiver chain, yeah. So we also have there's been a nice model that's been done using the scikit RF, where we're trying to actually very carefully ascribe attenuations and temperatures and losses the whole way up the chain, RF chain, and just making sure that we know from each signal path that we have a good understanding of each of those. And it really just comes down to what our confidence level is. So this has been it's the simplest thing to do, but it's still tricky. You also, one of the things we found is that if you have too much heat on this, then out of band power will actually saturate your amplifier and cause you to, mismeasure. And so we've been looking at filtering some of that out of band power as well.
This was the main question. Amplifiers
Yep. There's linearity checks and making sure that we're getting a linear response. Gray and Chelsea really dug into this, when we were doing our. It's been a lot of discussion, and so our colleagues at Washington University St. Louis are looking at a new hot cold load, and we're looking at trying to quantify how high we can go, and if we can do some low pass filtering to remove any of that out of band power yet. But I don't think we've been able to put that. So it's been limited to how hot we can make it while still keeping the JPAs linear. It's a challenge. Yeah.
So for the with the 18 cavities that we also you mentioned that the scanning speed increases linearly with the number of cavities. That's not just due to the scanning speed.
And I should say that's relative to doing individual cavities that are not co-combined. So that was a comparison, and maybe that was a subtle point. So there's a volume aspect of it, but if you just had individual cavities that are not coherently combined, you're going to slow down because your signal noise ratio isn't as high. Whereas because we're relying on the Axion being at the same coherence, same phase versus all the noise, you can get a square root of n enhancement to the signal noise ratio. And our scan rate goes as the signal noise ratio squared. So
And how do you do this technically? Do you actually do mixing of the signal, or do you do it?
we have a fully digital, like in phase addition of the system. And we'll be doing signal injections, when we tune to the new frequency as part of our data run plan, you do a sweep like that, the transmission measurements to make sure everybody's lined up and that we're getting the same enhancement. And then you sit and take data like that and then add the signals up. Yeah. So it is crucial as we get to like mini cavities to be able to boost it versus individual, incoherent runs. So there's been other, discussions about trying to do like frequency multiplex search where each cavity has its own small frequency range and maybe you can only tune like using non-mechanical tuning methods like kinetic inductance or something like that. And then so that's kind of like a frequency comb, but then you lose that enhancement from the Axion signal. As you tune, like you mean during tuning or like we usually only move like a kilohertz. Yeah. We have to stay within, I think the number we came up with is about 10% of a line width for each one of them. So it's a challenge, especially as we go to high Q cavities to make sure that vibration, everything else keeps them within 10% of a line width. So, it'll be, right now we're at kind of 10 kilohertz line widths. If we get down to 1 kilohertz or less with superconducting cavities, then we're going to be within a few hundred hertz at most. And we wanted them to stay that way for hundreds of seconds as we integrate. So it's a metrology challenge, yeah. The nice thing is the magnetic fields tend to, at least we've noticed in our systems, tend to dampen out vibration a little bit. So it sometimes helps at the expense of heat. Other questions?
Very basic question myself. The figure of merit that you showed at the beginning, that is basically the
Scan rate, yeah.
It's proportional to the Q, the cavity.
Correct. Let me back
This
there.
is because you have amplification of the signal, but you lose part of it because you need to have more steps.
Yeah, exactly. Yeah.
Now with the new results that can have very high Q with the coatings and this very nice result from Casper and all that.
Yeah.
You can go to Q above the Axion Q.
Yeah. So then, one response to that is you can overcouple then, and so you can get more signal power out. So I think we would want to have as high a Q cavity as possible, and then we can just overcouple the cavity if we need to. The less we have lost to the walls, the better, in my opinion.
Well, what is the argument? Because you don't keep increasing the figure of merit in principle.
No, at some point, like you'll be limited by what your assumption is on the Axion line shape and such. But no, if you do increase it more, then I think you can overcouple and that increases your bandwidth. So you take larger steps. So I think it still does. I think you can still go a little higher than that. Yeah.
You still,
Yeah. We still want as high a Q as we possibly can. Yeah. Hey, Andrew. Oh, no worries. It's good to see you. Well, that's a good question. I think it, man, I have to remember this. We talked about this a while. I think it's, yeah, exactly. Yeah.
Because you're making assumptions on line with this fine line.
Yeah.
So well, I don't really want to understand. So it's not.
You end up with like choices that you have to make in terms of your, how much signal integration time, your time series length is, that kind of thing. Yeah. Exactly. So you can look at it as long as you integrate far out from the wings of your Lorentzian. Mm.
Yeah, so you're taking this.
Yeah, exactly. You could miss it. And the 10 to the 6 is a lower bound. Like so it could very easily be higher, right? Like
But let's assume that that's not the case. The relationship is
I think so. Yeah. I think if you, because you'd want to overcouple still. If you had like a 10 to the 13, so say we had a 13 million Q cavity like CAP has, I would think that you want to just overcouple to at a Q of 10 to the 6 or so. Yeah. We could discuss, yeah. Sure.
Right. Yeah, and I'm not saying if you have a 9, you know, relatively broad.
Yeah. We don't want to miss those. Yeah. Yeah. Okay. All right. Well, thanks everybody. Appreciate that.